Okay, so I think we're ready to get started. I guess people might continue trickling in. This is a bit of a challenging one with the different time zones, but my understanding is it's quite early in Japan right now. So thank you to Yuto Mochizuki for joining us for our monthly seminar. Welcome to everyone. My name is Alex David Duras, and it's my pleasure to introduce Yuto Mochizuki from the Institute of Space and Astronautical Science at JAXA. Mochizuki-san is involved with the XRISM team, and today we'll be talking to us about some work that was done, very nice new XRISM results regarding Centaurus X-3. So without further ado, please take it away.
Okay. Okay, thank you very much. Hello everyone. I'm Yuto Mochizuki from JAXA. Thank you so much for the invitation, and I'm honored to have the opportunity to present at this seminar. So today I will present the observation result from the XRISM satellite, and I'll first talk about the past topic, detection of the origin modulation of iron for emission lines. And if time permits, we'll also cover the other topic, plasma diagnosis using line intensity ratios. Okay, this is the outline for this seminar. So first, I will briefly introduce myself. So my name is Yuto, and I'm PhD course student, and my supervisors are Ebiso-san and Tsujimoto-san. So these are the this is one of my favorite picture taken during the XRISM ground test. I participated in the test and contribute to the XRISM project. So, and my research covers three main topics. And number three is the main topics in this presentation. But I will briefly talk about the one and the two topics on one slide respectively. So first is a X-ray analysis of active reactive nucleus. So Mercurius-661, one of the narrow line Cepheid-1 galaxies, is one of bright AGN in X-rays, and shows blue shifted absorption lines along with the broad iron emission lines. So this figure shows the results of spectral analysis in the X-ray. So in addition to accretion disk and torus reflections component, we also need to consider slightly broadened Gaussian lines shown in cyan. So this is consistent with the hydrodynamic simulation for ultra-fast outflows presented for working on Mizumoto-san's paper. And we propose that the broad iron emission lines originated from the scattering emission lines from ultra-fast outflows. And we propose the geometry of narrow line Cepheid-1. Okay, and the second is the event screening of XRISM resolve. So we optimized and developed the X-ray event screening process to minimize background events. So this figure shows the background non-X-ray background spectra of X-ray XRISM resolve. So blue colors shows the unscreened background. So we optimize the initial screening, which means event screening using the standard pipeline, and we confirm that it satisfies the requirement shown in orange. So additionally, we developed the optional screening. So after applying this screening, the background spectrum shown in green is significantly reduced, And so that so MXV decreases by half with minimal loss signal. Okay, all right. Next I will talk about the main topic, detection of the modulation or iron alpha line in a segment 3 using XRISM resolve based on our paper. Okay, this is outline for this topic. First, I will introduce the binary system and the XRISM resolve instrument. Okay. Eclipsing high-mass X-ray binary pulses consist of a massive star and a neutron star. So the neutron star accreted material through wind or disk, and then radiated X-rays. So there are many common physics processes with other systems, such as AGN or something like that. But eclipsing high-mass X-ray binary pulses have 3 observation advantages. So first is a spectral variation around the orbital phase. So this allows us to see the 3D structure from different viewing angles. The second is eclipse. So this allows us to separate the incident and reprocessed X-rays. So third is a pulse resolve spectroscopy. This allows us to estimate the distance metric. So BX1 and SNX3 eclipse and high-mass X-ray binary pulses, and these objects were already observed in the PV phase of XRISM resolve. So in this object, SNX3 is one of the brightest objects. So the massive star is O-type star, O6 probably, fitting its rush lobe. The orbital period of this system is about 2 days, and the spin period of the neutron star is about 4.8 seconds, and the orbital separation is about 10 times the light crossing distance during one spin. Okay, and I would like to show you the launch moment of the XRISM satellite in the H3 rocket. So, so please be mindful for the volume. Can you hear that sound from the movie? I visited the Tanegashima Space Center in Japan 2 years ago, and I took the picture movie. So yeah, it was one of the most impressive moments in my life, and I hoped for the success of the launch because my master's and PhD thesis is very, very dependent on it. All right, the XRISM satellite is equipped with a resolve instrument in this here. And then image on the right shows the image on the right shows the resolve instrument. So when X-ray passes through the mirrors and detected by the X-ray detectors, which are cooled to 15 meters Kelvin by mechanical refrigerator. Since the cover is closed in orbit, so we are able to observe the energies above 2 kb. So this X-ray detector is called the X-ray microcalorimeter. So left figure shows the X-ray microcalorimeter on board XRISM. It consists of an array of 36 pixels, which with each pixel measuring 0.8 millimeter. The figure in the upper right shows the image of the pixel and the time versus temperature figure. So when X-rays hit the detector, the temperature of the absorber increase and exponentially decays over time. So, and the resistance of the temperature sensor in the absorber is sensitive to temperature changes. So by measuring the change in current, we obtain the digitalized pulse shape. Okay, and the pulse of X-ray events detected by the X-ray microcalorimeter are initially processed on board the spacecraft. So when the observed pulse is D, and so this is explained by the pulse height and normalized average pulse and noise spectrum. So through the least square method, so determine the H value, then minimize the chi-square and enable fitting D, which allow us to obtain the arrival time, energy, and so on. Okay. And the X-ray camera in resolve, it have the several advantages. So first is provide high energy resolution, more than 10 times higher that of CCD detectors, and about 3 times higher than that of grating detectors. So, and it has unique energy dependence of energy resolution. The left figure shows energy versus energy resolution, E over delta E, highlighting the resolvable Lyman series, Lyman alpha, beta, gamma. So the dashed lines represented the grating detector, and this line shows the resolve. So in case of grating detector, the energy resolution follows the dependence of e to the power -2, which means that energy increases, the resolution decreases significantly. However, in case of X-ray microcalorimeter, E over delta E follows a dependence of E, so meaning that the resolution remains high even at high energies. So resolve is capable of resolving fine structure, such as those found, such as iron lines and so on. Yeah, this capability is important for understanding the photon plasma. Okay, second has a large effective area, even with the cover closed, so comparing to the grating detectors. So the result is have the 180 square centimeter, like that. And it has a low background level. So result is able to detect lines even during the phase, like eclipse. All right, let me introduce XRISM result observation of SEM X-ray. We conducted the In PV phase, we conducted the fast observation covering entire orbit using a XRISM resolve XRISM spectrometer. So this figure shows the light curve and the background level of resolve. The exposure time was about 200 kiloseconds, and we achieved high observation efficiency. And 2 eclipse and here and some dips observed above background. And the detected total photon is about 9.3 million events. Okay, next I will introduce the result. These are the results of the orbital spectral variation, both in and out of eclipse. This figure shows the spectra from resolve and Chandra heterogeny with grating detector. So as you can see, the left figure, we can clearly separate the lines in iron K alpha and helium alpha XYZ, WXYZ, and the Lyman alpha in and out of eclipse state. The line ratio are different, and ionization line intensity in eclipse are relatively higher than out of eclipse. Comparing with iron K alpha line, and it means that photons plasma is more extended than the size of Oyster. And additionally, line profile out of eclipse showed unresolved and p-signal profile. Okay, next result of the orbital dependence of the spectrum. So for the first time, we obtained well-exposed spectra at each orbital phase. So the left figure shows the spectra, so energy versus orbital phase. And we observed the fluorescence lines caused by cold material and ionized lines caused by hot plasma. So we found 3 main findings. So first, the line center is modulated by orbital motion. And second, intensity of emission and absorption lines changes, indicating that line photons are scattered by material. And third, we can see the p-signal profile in some orbital phase. This feature reflects on the velocity structure of the system. So in this study, in this topic, we focus on the orbital motion of a line center orbital motion. Okay. This figure shows the orbital phase and radial velocities of the ionized ion lines. So plus value of RV means a blue shift and minus means a red shift. So orange dot shows the result of iron helium alpha, and magenta dot show the result of iron lime alphas. So as you can see, there is no clear modulation. So it suggests that they do not show the orbital motion and originate from the more extended region than Oyster. Okay. On the other hand, black dots show the result of the iron K alpha lines. So we found clear orbital modulations in the iron K alpha emission line for the first time. So we fitted the data with the sine curve like that and estimate the radial velocities amplitude to be 215 km per sec, and phase offset to be known. And the red curve shows the radial velocities of the neutron star, assuming as the Kepler velocity. And this velocity is 391 kilometer per second. As you can see, the radial velocity of iron Kepler is significantly smaller than that of the neutron star. So it suggests that the iron Kepler does not originate from the vicinity of neutron star. We also observed the spin spectral variation. So we obtained the spin phase resolved high resolution spectra with sub-second resolution in left figure. The right figure shows the pulse profile in the 7 to 8 kb range, shown as blue, and the iron Kepler energy band. The pulse fraction of iron Kepler is smaller than the 7 to 8 kb range. So it suggests that the line photons are spread over the phase and originate from the slightly extended region. Okay. Next, I will discuss the origin of iron Kepler. Since this line does not originate from the vicinity of the neutron star, so can it come from the all-star surface? To explore this, we calculated the radiative transfer using SCART. So we assume the 3D rostral structure for the all-star and point source for the neutron star, like left figure. The right figure shows the observed and simulated result of iron Kepler's equivalent width as a function of orbital phase. Now, as you can see, the simulation does not match the observation. So it suggests that the iron Kepler also does not originate from the all-star surface. So in conclusion, we can create a picture of Centaurus X-3. The red circle shows the photonized plasma around the neutron star, extended more than the size of all-star, originated ionized iron lines. And on the other hand, iron Kepler emission lines originate from the slightly extended cold material between the neutron star and all-star as green structure like accretion flow. And we have constrained the geometry of the iron line emission region around the neutron star. Okay, conclusion. This is the conclusion and the key result in my past topic. And we observed the entire orbit with a high resolution X-ray spectrometer for the first time. And we can see the clear line separation. So clear line separation was observed in complex iron lines, Kepler, Heliomarper, Ramarper, and both in and out of eclipse. The well-exposed spectra at each orbital phase were obtained for the first time. And spin phase resolved high-resolution spectra were obtained with sub-second resolution. And we constrained the following things. And the radial velocity of Heliomarper showed no clear orbital modulation, and the intensity are comparable to iron Kepler during eclipse. It suggests that these ionized line emission line regions are more extended than the size of all-star. In contrast, the radial velocity of I don't care for shows clear orbital modulation, but the amplitude is smaller than that of the neutron star. And the equivalent width of I don't care for as a function of orbital phase does not match the reflection from the surface. Additionally, I don't care for shows that smaller parts fraction than the 7 to 8 kb range. So the I don't care for emission region is not a neutron star and not Oyster, but somewhere between neutron star and Oyster. Okay, this is first topics. So if you have question and comments, so please ask me. Okay. Or I will continue the next topics.
Oh, we have a question from Matsuo.
Oh, yeah. Thank you for a very interesting talk. And I have two questions about K-alpha line. Okay. One thing is that XRISM detected K-alpha line even in eclipse, right?
Yes.
Yes, and you said that detection outside the eclipse means that the emitting region is bigger than the O star. But it seems to me that your conclusion about the emitting region is, I mean, smaller than the O star. So how does it is it consistent with the, I mean, detection of the K-alpha emission during the eclipse?
Yes, thank you for the question. Yeah, true that during eclipse we can see the I don't care also I don't care for lines emissions. So during eclipse, I think the I don't care for lines come from the scattering material and extended Oyster or the scattering from the cold material and compton scattering, electron scattering, and to the observer.
So
yeah.
the origin of K-alpha emission is both of cold materials and photoionized plasma.
Yeah, mainly I think that from cold material because this material have the high electron densities, so suggested by the hydrodynamic simulation, like give it a sec. Can you see my side? So this way, this like that. So you just moving around the Oyster and accurated the material by the stellar wind and Roshrov overflow. And you just accurated the material like a comet. So that this region of the high electron density and the crown density. So the idle caliper probably come from this structure, I think.
Okay, thank you. And my second question is about the line profile of K-alpha line. It seems to me that the observed profile is not clearly a single peaked, but it can be a double peaked profile because some profile shows double peaked and some profile shows a wide top wide more or less flat top. So do you think accretion disk, if the emission line is a double peak, then it seems to me that accretion disk is also a candidate of the emitting region. So what do you think about that? Accretion disk can be a emitting region?
I don't think so. You mean if we observe the double peaks of the IRK alpha, so that's line should not be come from the accretion disk, right?
Oh no! It's
And
coming from a rotating body, so accretion disk is a candidate.
candidate, yeah. Yeah, I will not deny the possibility, but so radial velocities amplitude of the iron curve shows 250 kilometer per sec. So to explain this amplitude, the and phase offset is about 0. So that's material is around material orbital modulated with the neutron star. So if disk origin is disk, so it's too vicinity, too close to Oster. So this cannot explain the radial velocity. So
Okay.
I just think so the origin of the accretion disk.
Okay. Yeah, I was thinking that if an accretion disk is very asymmetric or strongly elongated, then yeah, maybe it can explain the significant lower velocity, but it's just my idea. So thank you for your answers.
Yeah, thank you for question.
Do we have any more questions for this first topic? Okay, so maybe we can move on to the second topic then.
Okay. Okay. I will talk about the second topic, plasma diagnosis using line intensity ratios. So these topics we focus on the during eclipse, not out of eclipse, and use the line intensity ratios and to estimate the plasma geometry and UV luminosities. Okay, this is outline for this topic. So first, I will introduce the UV line driven wind and our ratio and aim for this study. Okay. So I will start the AGN interaction. So I will narrow Cephatron galaxies exhibit a UV hump like that. This one, and we cannot observe this range, but this one. So from the accretion disk and iron emission lines from disk or outflow, and ultrafast absorption lines from originate from the ultrafast outflows. So UFOs are accelerated by various mechanisms, like radiation or the magnetic mechanism. So one of them is line-driven accretion, acceleration. It's where momentum is atom gained momentum when the UV photons radiated the more atoms and bound-bound transition. So understanding how the wind is accelerated by these line-driven processes is important to reveal co-evolution of agent and host galaxies. Some study suggested the correlation of the supermassive black hole masses and stellar mass system velocities. So the left figure shows the X-ray spectrum of the ultra-fast outflow source observed by XML Newton. So currently UV luminosity is estimated by the modeling assumed neutron luminosity like other physical parameter. But so estimating the UV luminosity is challenging. So due to the interstellar medium or the host galaxy, because then due to the absorption. So the independent method to estimate UV luminosities is key to understanding the line-driven mechanisms. Okay, one method to estimate UV luminosity is by using the R ratio. The R ratio is defined as the intensity of the forbidden line over the intercombination line intensities. So for iron, the transition energy from 3s1 to 3p2 or 1 is a few 10 of electron volts. So which makes it possible to excite the line, excites from this level to this level by UV radiation. So Porter Quadrant 2007 have shown the UV dependencies of the R ratio through radiative transfer calculations. As shown in the figure, the R ratio decreases as the UV luminosity increases because of UV excitation effect. Okay. In this study, our aim is to establish the methods to estimate the UV luminosities using the R ratio of helium-like ion lines and radiative transfer calculation, RT calculations. And the target is needed to already know the UV luminosities and highly ionized ion in X-rays. So the high mass X-ray binaries, this is SNXC, but it's an ideal target. So, and we use the XRISM resolve because it's capable of resolving the fine structure of iron, helium-like iron lines. And additionally, the plasma is no longer in local thermodynamic equilibrium LTE due to the strong radiation from the neutron star. So the charge and level population do not follow the Saha and Boltzmann equations. So we have to calculate the radiative transfer. So we performed the radiative transfer calculation using Crowdy. The Crowdy is a two-stream solver for RT. Okay, again, I will show you the observational SNXC with XRISM result during eclipse. So this is a spectrum during eclipse of Centaurus X-3. So we can clearly observe the processed emission lines from the photoionized plasma because the X-ray from the neutron star are blocked by the O star. So we use this spectrum. So, and the fine structure such as helium alpha XY and lima alpha beta 1, 2 were detected for the first time of the X-ray binaries. So we use the spectrum of change eclipse to estimate the line intensities. Okay, now I compared the observation result and simulation result at radiative transfer calculation. So I will introduce the setup of radiative transfer calculation. So we input the SED burning with the UV ratio into the cloudy. The UV ratio is defined as the black body flux from the Oster divided over the power of flux from the neutron star. The black body temperature is 35,000 Kelvin and the photon index is 1.3. As this is estimated from the out of eclipse observations. And the energy range is from 1 to 1,000 joule. So the plasma's positions depends on the UV ratio. For example, when the UV ratio is small value and the plasma is located closer to the neutron stars. And on the other hand, where the UV ratio is large values, the plasma is located closer to the O star. And additionally, since the local flux depends on the ionization parameter, so we adjust the ionization parameter to match the electron temperature. So this temperature was estimated using the lima alpha over helium alpha intensity ratio. And the carbon density and the electron density is also estimated by the and carbon density is estimated by lima alpha 1 over 2, and we assume the stereo wind and we assume the electron densities. So the left figure shows the output spectrum from the cloudy as an example. So comparing the case with UV ratio set to 0 and 10 to the power 8, we can see that the intensity of Z line decrease while the X and Y line increase as the UV ratio increase. And then we compared the observational result with the simulation result. The observation result are shown as dash line. It is mean values, and with error bar indicating the 3 signal uncertainty. The dot line shows the simulation result. So as you can see that as the UV ratio increases and the R ratio decreases due to photoionized plasma, because the electron density is significantly smaller than the critical densities. So R ratio only depended on the UV flux, the UV ratios. So as you can see this figure, and we can limit the UV ratio. So the UV ratio is upper limited to the 10 to power 5 to this one. So which means that UV luminosity is not quite high in the local regions. So then we also upper limited the UV flux. Okay, let's move on the discussion. So then we confirmed that the estimated limit value is reasonable. So to do so, we plotted the UV ratio contour on the orbital plane, this figure. So the left figure shows the orbital separation of the all-star orbital plane of the all-star and neutron star normalized to the orbital separation. So the UV ratio in the vicinity of the neutron star, vicinity of all-star, which shows the upper limit. Vicinity of all-star is high, UV ratio shows the high value, but upper limit value is the 10 because neutron star emits the X-ray. And since the plasma size cannot be smaller than that of the all-star because during eclipse, so we cannot see these plasma size, so that we can evaluate the lower limit of UV ratio to be 0.25. And additionally, we plotted the electron temperature, assuming a stellar wind in the red dashed region, like that. And when the UV ratio is 0.35, shown in magenta colors region, it is consistent with the estimated electron temperature and other limitations. So that's we constrain the plasma geometry and confirm that the upper limits for the UV ratio, so and estimated using the R ratio is consistent. Okay, and conclusion, and our aim to establish the method to estimate UV luminosity using the R ratio and the radiative transfer calculations. As a result, we have estimated the electron temperatures and constrain the local UV flux using the R ratio and the geometry. So currently we are working on the determining the simulation mass theoretical R ratio and deciding which solver to use. We are trying to completely establish this method. Okay, and okay, I remember on the future works. Yeah, this is a final slide, so it's about future works. So the radiation force acting on the rings consists of two main components, so electron scattering and line-driven accelerations. The contribution of line-driven acceleration is typically described using the force multiplier as shown in these equations. These force multipliers should be influences not only by UV radiation, but also by X-rays. However, the effects of X-ray radiation is included, now included phenomenologically using the ionization parameter or the optical thickness and so on. So to deeply understand the line-driven mechanism, so we have to include the effect of X-rays. So I plan to model the Centaurus spectra and out of eclipse the piecing profiles. So using hydrodynamic simulation and combined with radiation transfer calculation, and I would like to estimate the more reasonably for the line-driven mechanisms equations. That's it. Thank you very much.
All right, thank you very much, Mochizuki-san. Everyone join me in congratulating on a very nice talk. So we have some time for questions. If people have questions on either this latest topic or the whole presentation. So maybe I'll use my prerogative as the host to ask you a question about XRISM. And of course, I don't know how much you can tell us, so please feel free not to answer. But do you know, I haven't heard about this in a long time, but my understanding was that there might be some efforts to somehow open the cover. Do you know what the status on this is?
Yeah, maybe XRISM team will try to open the cover in September or maybe September. So XRISM team they will vibrate the something to open the covers. So I don't know the possibility to the success or success, but yeah, I really hope to open the cover because the XRISM result have the high observation efficiency and the wide energy range. This satellite is able to observe wide range because the result is a low background. So after the gate bar, after cover opens, we can observe the 0.1 Kelvin. So we can observe the carbon emission lines and the absorption lines. So yeah, I really hope to open.
Great, thank you. Are there any other questions? Okay. Well, in that case, please join me in thanking once again Mochizuki-san for a very nice presentation. And I'd like to remind everyone that, as always, the video of this presentation will be made available on YouTube in short order. So if you have colleagues that you think might be interested in this but could not connect for some reason due to time differences or something, please feel free to share the link to them. And the talk for next month will be announced shortly as well. So stay posted for that. All right. Well, thank you very much, Mochizuki-san, once again, and have a very nice rest of your day or night, as the case may be, depending on where you are. We look forward to seeing you again.
Thank you very much.